Ladies and gentlemen, welcome aboard. It is my great pleasure to say hello to our Ask a Physicist series. This series consists of several activities. One of them is a series of lectures with renowned scientists who are talking to everyone, irrespective of how well they know contemporary physics. All that counts is the enthusiasm. They talk about interesting physics. And today's lecture is going to be very interesting, but this is not my job to introduce the speaker. I would like to point out that we have a second line of activities here, and this is the website, which is also called Ask a Physicist, where you can ask any question you always wanted to ask about physics, but you are always afraid of doing so. So there is no reason to be afraid. We have a staff of volunteers who are very willing to answer any question that might come. And very often we are, as physics professors, very perplexed by those questions because they are so deep, they help us develop our science. So don't hesitate. Send us your questions and we'll do our best to select those that we can answer. We cannot answer all of them. Some of them repeat, but to some of them we don't know the answers yet. But without further ado, I would like to ask to say a few words Professor Maciej Lisicki, who will introduce tonight's host.
Thank you very much. And I think, so some of these questions that are yet unanswered and the questions that you might pose on this website have come to you while in the kitchen, while doing the dishes, while cooking, and while just observing flows in the kitchen. And there's plenty of fluids there, and therefore there is also plenty of interesting questions that might come to mind. And so it is my pleasure to introduce to you Arnold Mathijssen, who undertook the task of explaining some of these phenomena that we can see in the kitchen and that often inspire scientific questions. But it's also a story not about gastronomy inspiring physics, but also the other way around, about physics inspiring gastronomy. And so a few words about our speaker. Arnold Mathijssen is an assistant professor at the Department of Physics and Astronomy at the University of Pennsylvania. But before that, he was at Stanford University, and even earlier than that, at University of Oxford. And I think we met at a conference, and then we kept meeting at probably a dozen or so of different conferences until we decided to work together. And this is one of the topics that got us really excited to work together. And I think we're both happy that this is taking the stage now. So let's welcome Arnold to give us a tour of the kitchen phenomena.
Thank you very much. Thank you. So first of all, really a big thank you for welcoming me here in Warsaw. I've had a wonderful time since last week. I've had the honor to explore your department and to explore your city, and I must say I'm just really amazed. So before I begin with the presentation, I have something practical that I would like to do. Over here we can see a couple of boxes of pasta, which I'm going to give to you, and we're going to do some experiments later. So what I would like you to do is to take maybe say 5 or 10 pieces of pasta and then give it onto your neighbor.
I'll help you.
And then hopefully we can reach all the way to the back and see, there should be plenty, there should be enough. So if you take 5 or 10 straws each, then we would have enough. And then, maybe in about 20 minutes or so, we're going to do some experiments with the pasta together. So take your time, pass it around the room, and then we should have all the opportunities.
And I will interrupt for one more moment, just to say that it's the lecture is here for you. So if any questions come to your mind, please do ask them. And in particular, if a question comes to your mind that is a question in Polish that you would like to see translated, we are happy to help with that. So independently of or irregardless of the language, please do ask questions.
Exactly, yeah, please ask questions anytime. I'm more than happy to answer them. And also you can ask questions afterwards or send me a message if that's more comfortable as well. So are you ready to get started? Yes, are you ready? Okay, cool. So I want to talk about culinary fluid mechanics. Now, fluid mechanics is the study of flows, and flows are really everywhere around us. Here we see a picture of a cup of coffee on the left-hand side, or we see an airplane here on the right. And these flows are everywhere, but they are often hidden. So we can't really see what's moving in these pictures, right? They seem to be static pictures. But if I click on this button, you'll see that we can actually visualize the flows that are happening around these objects. Here on the left-hand side, we have airflow that rises up around this coffee cup because the coffee is hot. And this hot air is going to rise up, and it's for that reason that we can actually smell the coffee in our noses. Similarly, here on the right-hand side, we've got the airplane, and because of the flows that are happening around the wings of the plane, it's pushing the air down, and as the plane is pushing the air down, it's pushing itself upwards. So these flows are everywhere, but they are hidden, and we need some techniques in fluid mechanics to understand how exactly the flows are formed, and then what forces and what consequences these forces have in the world around us. I said fluid mechanics is everywhere, and that also means it's everywhere in industry. It's used, across many different areas in the economy, maybe in terms of the chemical industry, renewable energies, windmills, water management. And therefore, when we study fluid mechanics, we try to study universality. We try to study properties of flows that apply not only to one thing, but that apply to many different sections in physics and many different sections in our economy and the world that we live in. So I would like to study fluid mechanics using food science. Why do I do that? Well, there's a couple of reasons. First of all, there's a whole lot of creativity in the kitchen. So we can do creativity by cooking, and chefs are being creative every day when they prepare new dishes and they try to be exciting on their menus. But science is very similar, isn't it? We try to be creative in our science, come up with new ideas, and actually the only way to make new discoveries is to let go of old ideas and to have new creative inspiration. So I think that the kitchen can be a creative environment that can help science, and at the same time, science can help food scientists as well. Another reason is that kitchen science is really accessible. It's something that doesn't need expensive tools in a laboratory. You don't need all the consumables that you buy from these companies. You can really just go to the supermarket, get relatively inexpensive ingredients, and that lowers the barrier to science. That makes it more accessible to people who cannot necessarily afford to have a more expensive education, and instead they can learn about science in the kitchen. They can ask questions, and they can then take their ideas further. Another reason is that we can make science more equitable for that reason. We can try to support minorities in physics and minorities across all the fields of sciences. And to make that a little bit more explicit, I have an example for you, a striking example. I want to talk about the legacy of Agnes Pockels. Agnes was a woman who lived in Germany around the 18th century, and she didn't have a job. She worked at home. She would cook in the kitchen a meal, they would eat, and then afterwards she would do the dishes. Now it turned out that when she was doing the dishes, she was studying soap films. So she was very systematically studying soap films. She was really looking at the forces that hold bubbles together and the forces that we now call surface tension. And while she was doing this, she made a discovery. She discovered that surface tension can be measured with a special type of machine. And that machine we now call a Pockels trough. And this invention is still used today in modern laboratories, and it's one of the most fundamental machines to measure surface tension in the area that we now call surface science. So she made this discovery, and she tried to publish it. She tried to send, publications to various journals in Germany, and she got rejected again and again because she was not a professional scientist. She was just working at home in the kitchen. And so she didn't know what to do. She was stuck. But she knew other scientists that were working in this field, and one of them was Lord Rayleigh in England. And in the end, she thought maybe I could send him a letter and just share my results with him, and maybe it's useful to him. So she wrote this letter that goes as follows. My lord, will you kindly excuse my venturing to trouble you? And then she explained all the discoveries that she made, and she explained the device that she invented in a lot of detail. And she effectively gave her ideas away. And then she ends her letter, and she says, well, I thought that I ought not to withhold this from you, all these things that I've observed. And although I'm not a professional physicist, I'm again begging you to excuse my boldness, and I remain, with sincere respect, yours faithfully, Agnes Pockels. So she gave her ideas away, but Rayleigh was really impressed by this. And he actually helped her to translate her work from German into English, and he sent it to a journal, and they published it. And this journal is called Nature. And since then, she really had a big breakthrough. She published many papers, all in Nature, Science, all big, fundamental achievements in a field that we now call surface science. And as a result, she started a whole new field in interfacial flows. And this is really the foundation of what we now call nanotechnology. Because interfacial flows and surface science is one of the most fundamental forces at the nanoscale. And so when we do all of our microfabrication today and we do all of our nano techniques, we rely on the techniques that were designed by Agnes Pockels in the 18th century. So this is a story that tells you that, yes, science can help with making our food better, but at the same time, creativity in the kitchen can also help science, can lead to new discoveries, and really can lead to fundamental breakthroughs that are not just important in food science, but are really fundamental to discoveries in things like nanotechnology and the world that we live in today. This is just one example. And what I would like to do today is to give a talk with the following structure. This is the overview of my presentation, and I've structured it a bit like a menu. So first we're going to talk a little bit about drinks and cocktails, and then we might have, a soup for starters. Then we have the main course. We're going to cook some pasta. I hope that the pasta has now spread around the room. And do you all have like 5 or 10 sticks of pasta? Yes? Okay, if you don't have pasta yet, then there is pasta right here. So we're going to cook pasta together, okay? And then we'll have some dessert. We have some coffee after dessert, and then I'll sum up. You guys ready? Okay, good. So let's begin with some drinks. I want to begin with drinks at a very early time. What we see here is a picture of what's called a Tantalus bowl. And this is part of a treasure that's called the Vinkovsky treasure from the late Roman period. So it's over 1,000 years old. Now this bowl is rather special. You can drink wine out of it. It's made to drink wine out of. But at the same time, it's a practical joke device. So what happens in this bowl is that under the statue over here, and I'll try to put with the pointer, there is a tiny little channel. And if you fill this bowl up with wine, then initially nothing happens. You start filling it up, and you can drink out of it perfectly fine, and it's really a beautiful cup to drink out of. But if you put too much wine in the cup will empty itself. The wine will flow out of the cup through that hidden little channel, and if you are too greedy, you will get nothing. So here is how that works. Here there is a modern reconstruction of this Tantalus bowl, and when I play this video, you'll see we pour in some water, nothing happens. You can drink out of it perfectly fine. Pour in some more water, nothing happens. But now, there's a critical moment. You put too much wine, and the cup will start emptying itself. So, here is our Roman who says, "Where's my wine?" And the cup replies to you, No, you've already had enough. This is it. So you can see that fluid mechanics was already there, right, thousands of years ago. And in fact, it's because of fluid mechanics that people started irrigation, that people started agriculture, and that we could do the production of food at larger scales. And it's because of that that we started our technology in fluid mechanics. So when we look at maybe a glass of a bubbly drink, let's say a glass of beer or some Coca-Cola, anything you like, then there's a lot of physics happening in here, right? So on the one hand, you know, we might have some foam here at the top, and that foam can help you because on the one hand it gives you a lovely creamy texture, but at the same time it also helps with temperature insulation. So if you like your beer to be cold, then this foam has beautiful air pockets that's going to help with insulation, that the heat from outside doesn't go down into your glass. There's a lot, excuse me, there's a lot more physics happening over here as well. You can see these bubble trains. Let's see if my pointer works. I try to move it in this way. Well, they start as very small little bubbles at the bottom, and then they start growing larger and larger as they go upwards. Why does that happen? Well, it's because there is CO2 that's dissolved into the liquid, and it's actually supersaturated. So there is too much CO2, and therefore it wants to come out of the liquid. It wants to go down into the gas phase. And therefore, if you start with a little bubble, it starts capturing more and more CO2, and then the size of the bubbles gets larger. And to understand that properly, you really need to have, you know, a full understanding of the thermodynamics and the kinetics of what's happening in these glasses. Then, once these bubbles get bigger, they start rising faster as well, and that's all about fluid mechanics. That's all about the drag forces and the drag coefficients that we can try to calculate for these bubbles. Then, you can ask the question, why do these bubbles form in the first place? Well, there are very small nucleation sites that happen sometimes on the glass or just like small particles that are floating in the liquid, and that help with overcoming this potential barrier for the gas molecules to come out of the liquid and to form bubbles in the first place. Then sometimes the bubbles will actually implode. And then you get these very interesting dynamics of interfacial flows where a bubble kind of implodes and then it becomes big again. And that's all about the dynamics of flows at interfaces. And Agnes Pockels actually studied these interfacial flows. And then finally, the stability of the flows and the stability of the foam on top of the glass is determined, again, by interfacial flows. And so there is a lot of physics that you can study here that doesn't only apply to, you know, this glass of beer, but you can use it for many different applications as well. Now I have a question for you. What if I take this glass of beer into space? And, you know, imagine that you are an astronaut and you are floating around in the International Space Station and you would like to have a glass of beer, or you would like to have maybe some sparkling water. Then what's going to happen? What happens if an astronaut drinks a sparkling drink? What do you guys think?
Form a kind of foam.
Yeah. Yeah.
But there is no gravity. So
There is no gravity, yeah?
the bubble cannot go anywhere.
Mm-hmm.
Just inside, right?
Yeah. Yeah. And then?
Growing.
Keeps on growing, right? Yeah. I'll show you some pictures. On the left-hand side here is bubbles on Earth. Tiny little bubbles that are rising upwards. On the right-hand side, we have bubbles in space. And like you said, it just forms this one big thing. But it's not going anywhere because there is no gravity, so bubbles are not going to rise. Bubbles only rise because of gravity. And so if you're an astronaut and you've got this huge thing in your stomach, it's extremely uncomfortable, right? Because you have this very bloated feeling, and the gas doesn't want to come up. It doesn't want to go up and it doesn't want to go out. So unfortunately, astronauts cannot have beer in space. Yeah. so when they come back down on Earth, you really have to buy them a pint. Okay, cool. Now, I want to talk a bit more about bubbles. Here you can look at a glass of champagne. There is a laser sheet that is cutting through the champagne glass through the side. And therefore you can see all the flows that are happening inside the champagne over here. Now in a normal glass on the left-hand side, you can see that these flows are rather chaotic. That, you know, they rise upwards, but then you have all of this chaotic advection that happens inside the glass. Now what you can try to do is you can control all of these turbulent flows. And one way to do that is to create nucleation sites for the bubbles at one specific location. So what they did here is they've engineered a champagne glass. Let's See, the pointer is sometimes working, but not always. Yeah, okay. So here, at this location down here, they've created a lot of nucleation sites. And that's where all the bubbles are going to form. And therefore, you get this rising flow that goes upwards and then leads to this nice vortex at the top. And this is completely steady. It's not chaotic anymore. It's still a little bit turbulent at the top, but it's very controllable in this way. And the way that that works is, if you look very closely at the bottom of the glass, they've made a little ring here, and with a laser, you can create very nice little imperfections in the glass, and that's why the bubbles will rise precisely from these points. So what you then see is, from the side, the flow is rising up nicely and leads to these nice vortices. Or if you look at the top of the glass, then you will also see these beautiful spiral patterns that are forming. You say, okay, that's nice, maybe, fun to look at. But it's not only fun to look at. It actually turns out that the wine actually tastes better as well. Why is that? When the bubbles are rising up to the top interface, they will pop. And when the bubble pops, then it forms an aerosol. So you get these tiny little micro droplets that are injected into the air, and when you smell them, then that leads to all of this aroma and, better flavor of the champagne as you drink it. It turns out that when you control this vortex flow, you get more bubbles at the top interface, you get more popping, and you get more aerosols, and so the aroma is much stronger. And, a very simple change in the wine glass can then really change your experience. So next time you go out on a date night, I really recommend this. Okay, one more drink maybe, before we have some solid food. Here you can see a cocktail. What is a cocktail? It's a mixture, right? It's a mixture of water and, in this case, some alcohol. And what happens if you have a mixture of water and alcohol that evaporates slowly? The alcohol is going to evaporate faster. So at the top, you're going to have a very thin layer. Let's see if my pointer works again. Here, this blue color that you see at the top is a thin layer that has a very high water concentration and a low alcohol concentration, because the alcohol is evaporated, right? It's gone. And it turns out that the water is heavier than the rest of the liquid, and that water then sinks down into plumes. And you can study that. You can study that with lasers. So here, you can have a laser that goes through a beam splitter. One of the beams goes through the sample, and the other beam goes around the sample, and then you bring them back together again, and you merge them, and you look at the interference patterns. And what you see is something that looks like this, these beautiful fringes. And from this interference pattern, you can reconstruct with the computer an image that shows you the alcohol concentration everywhere in the glass, in space and in time. So this is what it looks like. The colors show the alcohol concentration, and you can see that the water is sinking down from the top because it's heavier than the rest of the glass, and it forms these beautiful plumes. Now, this is maybe interesting to look at. It can definitely improve your experience in the pub, but it actually turns out that this was a bit of a breakthrough experiment in studying what we call Rayleigh-Taylor instabilities. A Rayleigh-Taylor instability is really when you have a heavy liquid that's sitting on top of a lighter liquid, and it, is unstable. The heavy liquid wants to sink down. And people have done many, many experiments of Rayleigh-Taylor instabilities in so-called immiscible fluids. Fluids that do not want to mix, like water and oil. If you pour water onto oil, the water is heavier than the oil, and it will sling down. This has been very well studied. But in this case, we have water and alcohol, and the alcohol wants to mix with the water. And so it's much, much harder to study. And so this was really a breakthrough experiment to use these interference patterns with the laser to look at the Rayleigh-Taylor instabilities for, in this case, miscible fluids. And this had many applications as well, right? Not just in cocktails, but in any kind of cocktail, like industrial, chemical, reaction dynamics, where you always have these types of flows that are being generated. So this was like a really nice experiment that changed fluid mechanics in an important way. maybe we've had enough drinks now. I think it's time to move on to something a little bit more substantial. So, maybe we have a starter and we have maybe a bowl of soup. So, the soup is ready and it's ready to be served, but it's still a little bit too hot. And therefore, we need to stir the soup around a little bit before we can eat it. So we're going to stir the soup, and now what do we see if we stir some liquids, in a bowl? It forms a parabola. Because when you're spinning the liquid around, then you get all these centrifugal forces, fictitious forces, that are, bringing this liquid outwards to the sides, and it forms, a really nice parabolic shape. So you can think of that as a beautiful parabola. But parabolas, they have a focal point. When you shine light onto this surface, all of that light gets collected in one single point over here. And it turns out that you can use this. And people have used this to make telescopes. So here you can see the so-called Large Zenith Telescope. It's one of the biggest telescopes in the world. It's over 6 meters in diameter, and it's made of liquid mercury. So it's really just a liquid that you are spinning around in a big ball, and the faster you spin it, the smaller the focal point, and then you can put a camera exactly at the location of the focal point, and from that you can look out into space. It's one of the largest telescopes that we have on this planet, but it's also one of the cheapest telescopes, because you really just need a liquid that you're spinning around. The only disadvantage is that you can only look upwards. You can only look in one direction. And so, as the Earth is rotating, you can scan across the sky. That's all you can do. Then, of course, you can try to make more expensive telescopes using exactly the same method. So you can take a metal, you can heat it up in a big, furnace or an oven. Then you spin it. It will form a parabola. And then you cool it down. And then you get a solid metal that has exactly the same shape. And then you can turn it and you can point your telescope at any other direction. And that's how we make telescopes. We spin metals. We melt them and we spin them. Really expensive. So ideally you want to do it like this. Okay. So, going from very large, macroscopic, astronomical applications, I want to take you down to another technology at the micro scale. And to get there, I want to talk again about some kind of dish that now just has some water in it. And on top of the water, there's a little boat, just a piece of plastic, anything that floats. And then when you put a little bit of soap into the boat, then what you see is that the boat starts swimming. And it just keeps on zipping across the glass. Really nice to try this with children, by the way. You just need some dishwashing soap, anything that you can buy in the supermarket, and they're pretty fast. Now, it turns out that you can do this with soap, but you can do it with almost any mixture of two liquids. So you can also, do it with any other kind of fuel. And the way that it works is that at the back of the boat, you're releasing this fuel. And it turns out that this fuel has a different surface tension compared to the water itself. And so you create a gradient between the front and the back of the boat. And therefore, you get a propulsion force. You get a driving force that pushes the boat forwards. Or if you wish, the liquid is actually pulling the boat forwards from the front, because the surface tension of water is larger than the surface tension of the fuel at the back. And so you are pushing this boat or pulling it all the way through the liquid. You can do it with soap, but you can also do this with alcohol. And there is this group at MIT, and they've made these, nicely 3D printed little boat shapes. And then you can just take any, drink that you like, maybe some whiskey or some vodka. And you pour it down into the boat, and it will just zip across your martini glass. So it's a really nice party demonstration. It's a nice party demonstration, but it's also really useful because it's used actually in nanotechnology. Here you see very small droplets that are about 50 microns in size. They're smaller than a human hair. And you can make these droplets swim using exactly the same mechanism. You have molecules that have an imbalance. There are more molecules at the front and there are fewer at the back, and as a result, these droplets will start swimming. So here are some small microchannels, again, thinner than a human hair, and these droplets, they are just swimming by themselves, just like the little boats that I showed you earlier. And we can calculate precisely how fast these boats will go. So if you have no fuel, then the swimming velocity is 0. But then you add a little bit more fuel, and then suddenly there's a big jump in the velocity. They start going forwards and forwards, and then it saturates out to some level. Now this is nice because you can make small, say, micro robots. You can put maybe some drugs into these droplets, and then you can deliver those drugs to some location in the body, for example. And that's one of the main reasons why people are interested in making these little micro droplets. Another reason is that these droplets can solve mazes. So here you can see a maze, and we're releasing these droplets from the top left corner, and then there is an exit here on the right-hand side, and then there are some dead ends. So initially these droplets are exploring the maze, they're just going everywhere, but then they begin to realize, that area in the top right corner, that's not so good, that's a dead end, I don't want to go there anymore. And also, on the left, the bottom left corner, they don't really want to go there anymore. And instead, they find the shortest path between the entrance and the exit. So over time, these droplets are solving the maze. The way that works is very subtle. It's to do with the chemistry of the molecules around the droplet, and it's a bit of a self-avoidance reaction. So it's a bit like Hansel and Gretel, who are leaving the little breadcrumbs in the forest, and then eventually they're trying to find a path, and they're picking the breadcrumbs up where the previous droplets have been. And so they find the shortest way to the exit. Now, after having had a nice starter, it's time to do our experiment. It's time to, make some pasta. So, do you all have pasta? Okay, good. So, what I would like you to do is, I need some pasta myself. Thank you. Okay, great. So what I would like you to do is to bend the pasta, and then, very carefully bend it more and more, and I want you to break it. But when it breaks, I want you to see how many pieces do we get when it breaks. So when you break it, does it break into 2 pieces, 3 pieces, 4 pieces? Try a couple of times. You should have maybe 10 sticks or so. So try it a few times and see what happens. Break the pasta a few times. So what do you guys see? Maybe I can have a raise of hands. For how many people got 2 pieces? It only break in 2 pieces. Okay. How many people it broke into 3 pieces? Much more, okay. 4 pieces? Again, okay. 5 pieces? Still? 6 pieces? Yeah, okay. Do we have any more? 7? Okay, 6, you are the winner. So it turns out it's really very difficult to break the pasta into only 2 pieces. It always, it very typically tends to break in 3 or 4, sometimes 5 pieces. Here's the reason why. When you break this pasta, when you bend it, then initially you put a lot of energy into bending the pasta. And the moment that it breaks, then all of this energy is released, and it goes into vibrations. So if you look at this with a high-speed camera, you will see that this pasta is wildly going up and down. And because of these strong vibrations, a second piece will break off, and a third piece will break off, and maybe a fourth piece. So all of this elastic energy has to go out somehow. And it often leads to secondary fractures and third fractures. And so this is important because if you want to, for example, build a bridge, then you have a metal beam. Now, if the metal is going to snap at some point, then it might not break in one piece, but it might break in 2 or 3 or even 4 places. So if you then try to prevent this from happening, and you can try this with your pasta as well, if you wanted to break in only one location, you can try to twist it. So you take your pasta. I don't know if you still have any pasta left. Maybe you should take some more pasta. If you twist it and then bend it, well, I can't do it with a small piece, then the chances are much higher that it will only break into 2 pieces. So give that a try. Is it better? You really have to twist it quite a lot and then bend it. And then what happens that instead of vibrations, we're now going to get rotations. So all of this elastic energy is going to be turning into rotational energy, and that's going to prevent some of the secondary fractures. So maybe that's helpful, you know, if you can prevent secondary fractures, but there is a trade-off here. Here you can see a plot that shows, you know, how many times the pasta might break into 2, 3, 4, 5 pieces as a function of the twist. So here on the left-hand side, we have 0 degrees twist angle, and then all the way to the right-hand side, we've got 360 degrees twist angle. So you're really turning it a lot. What you see in this curve, that as you go from 0 to 350, then on the left you get, you know, all the, 4 pieces, 5 pieces, and then as you twist it more and more and more, you get more circles. And circles means that you only get 2 pieces. Sorry. At the same time, what you see is that the critical curvature, well, you know, how much force is needed to break the pasta is going down. So in other words, this pasta also gets more easy to break. So there is a trade-off. It gets easier to break, but it breaks in only one place. So if you're an engineer and you're making a structure, then maybe you want to introduce a little bit of twist, because then if it's only going to break in one location, you can put some secondary beams around it as a backup. And then you only have to, do maybe 3 or 4 backups and not 20 of them. But it's going to be a weaker structure overall. So there's some trade-off over here. Okay, so now we've broken our pasta, and then we're going to cook it, right? So when you cook your pasta, then you have to heat up some water. Now, you put your pot on the stove, the water is beginning to heat up from below, and then what you see are these beautiful patterns. Maybe you've seen this before. They're called Rayleigh-Taylor convection cells. So what's happening here? You're heating the water from below, and you're cooling it from the top. Now the hot water is going to rise, and the cold water, that's colder because of the air, is going to sink down. So you get these recirculations that are happening inside the pot. And exactly at the interface of those, vortices is where you see these nice sharp lines. And you can already see that. Maybe you'll try this evening at home. Look very carefully, and you'll see these nice convection cells form. There is a group at the University of Twente in the Netherlands. They have studied this in more detail using lasers. So again, they took a laser sheet, they cut through the sample, and you can see these plumes that are rising up from the bottom hot plate and then sinking down from the top cold interface. And then you can change the temperature, right? You can make this plate really hot at the bottom, And then the liquid goes crazy, right? It really starts boiling, and you see these like networks of convection cells that start to form. And again, this is really important for many applications because heating happens everywhere in industry, in chemical industry. And so sometimes you want this because then this convection maybe leads to mixing, and that's good for your chemical reactions. Or maybe you want to prevent it. Maybe you want to just keep your liquid as quiet as possible. So maybe in the case of our pasta liquid, we want to have a lot of mixing so that the temperature is nice and even. Then we put the pasta inside the water. What happens when you put pasta in the water? Well, on the one hand, it gets softer, hopefully, such that you can eat it. But it also gets longer. The reason why is because this pasta is basically a network. It's like all these little fibers that are sitting inside, and the water molecules, they will start penetrating in between the pasta fibers, and then it swells up like a gel. And so if you look at pasta after maybe 12 minutes, then it's already longer than it was. Then if you cook it a bit more, 18 minutes, it's even longer, and after half an hour, it's extremely long. It also gets much thicker. So there is this group by Huang et al., and they've actually studied this in a lot of detail. And here you can see how the water molecules are soaking and entering into this sponge, basically entering into the pasta sheets and getting thicker and thicker. So the swelling dynamics, you can see that after, between 0 and 33 minutes here on the right-hand side, you see that the thickness of the pasta is increasing by something like 70%. So the pasta gets almost twice as thick as the original uncooked pasta. And that's kind of agrees with your intuition, right? So that this is an uncooked one, which is a little bit thin, and then when you cook it, they get nice and round. The second thing is that it gets softer. So when you cook the pasta, then you can measure exactly how much force they can hold, and at some point this pasta will break. And you can also measure the elasticity of the pasta itself, and this elasticity we call the Young's modulus. Here is a plot of this elasticity as a function of how long you cook the pasta, and you see that initially it's very hard and stiff on the left-hand side, and then after 30 minutes it gets all soft and sloppy on the right-hand side. And you see that this actually goes down really fast. And this axis over here, the vertical axis, is logarithmic. So that means that the elasticity between the top and the bottom here is a factor of 10, 100, 1,000, 10,000, a million, 10 million. So you can really get a huge difference, maybe 6 orders of magnitude in terms of the elasticity after only, half an hour of cooking. And so the critical point, when you want to have your pasta al dente, is maybe around 9 minutes or so. What does it say on the package? 9 minutes. Okay, so yes, they've done the plot. If you do it 10 minutes, it might get 10 times softer. If you do it 11 minutes, it gets 100 times softer. So you can see you have to be very sharp with the timing. Yeah, like nobody wants pasta that's 100 times softer. That's awful. Any Italians in the room? Okay. they often disagree with me. Okay. One more thing you can do is you can measure the stickiness of pasta. So, it turns out that initially when you take the pasta fresh out of the water, then it's not so sticky. The filaments, they can just touch each other, and they're rather loose. But then, maybe after 12, 18 minutes, they start to stick onto each other, and then it's much harder to eat because then you try to twist it around your fork. It just it's much harder. So what you can do is you can do an experiment. You hold 2 of these pastas next to each other, and you see that they start sticking to each other. They start creeping towards each other, and you can measure the length of how much. How long is the separation length that the pasta is still free from each other. And that separation length, if you measure that, decreases again with time. And so after, say, 12 minutes waiting after the pasta is cooked, then yeah, they're really sticky already. So what that means is you cook your pasta in exactly 9 minutes, and therefore you eat it after exactly 5 minutes, and that's it. Okay? Good. Now, people have studied pasta a lot, and they've actually studied pasta in terms of shape-shifting materials. So here you can see some examples of creating three-dimensional structures from initially two-dimensionally shaped pastas. The way that works is you start off, let's say here on the top left corner with this bamboo structure. It starts off with a flat sheet, and this flat sheet has some, nice grooves into it. And now when you put this pasta into the water, it starts swelling, the volume increases, and then it has two layers. At the bottom it's going to swell a lot, and at the top you've got these grooves and it's not going to swell quite so much. So you have an expansion below and you have a contraction at the bottom, and therefore it starts curling upwards, and you get these nice bamboo structures. And now, of course, you can do that in many different shapes, right? You can make a helix, or you can make a little box. I like the box because that's like ravioli ready-made for you. Yeah? Okay, so basically, this is nice because then you can get very creative different shapes just from very simple two-dimensional geometrical structures. After the pasta, maybe we want, a bit of meat. And so here we are going to maybe grill a steak or a piece of bacon. But there's a problem often, right? Like this steak always sticks to the pan, and it's a huge pain. So what can you do to prevent this steak from sticking to the pan? Well, it turns out that if your pan is really hot, if it's like searing, scorching hot, then you hear this psh sound, and the steak will kind of hover on top of the pan, and it's not really going to stick anymore. And that is something that we call the Leidenfrost effect. So in the Leidenfrost effect, maybe you've seen this, if you put a droplet on a hot plate, then it's going to roll over it very quickly, or it will just sit right in the middle, but it's not evaporating. It's a very, very hot plate, but it's not evaporating. And the reason why is because this droplet is actually floating. It's levitating in the air, and there is a cushion, there is a pillow of vapor between the hot plate and the cold droplet. And so it's just hovering up there, but it's never really touching the plate. And so, as a result, there is not so much heat going up to the droplets anymore. Here there is a graph that shows you the heat transfer, the amount of heat that goes from the hot plate to the droplet. If I start here on the left-hand side, I start with a cold plate. Now I'm turning it up a little bit, making the plate hotter and hotter and hotter, and then, the droplet gets really, really very hot. But instead, if I have a really very hot plate, then the droplet doesn't touch anymore. And then the heat transfer is just very small. So that happens around 200 or 300 degrees Celsius, and that's called the Leidenfrost point. And that's the perfect temperature for your pan to cook your steak, because then your steak is hovering on top of the pan. It's not actually touching, so it's not going to burn, and you have a very nice low heat transfer without any sticking. If you make the pot even hotter, then of course, the whole thing is going to heat up very quickly again. So you want to perfectly tune it. You want to be somewhere around 200 or 300 degrees Celsius. Now the Leidenfrost again, this effect is used in many fun technologies, like at the micro scale. You can make droplets that have all these funky shapes. You can make star shapes, or you can manipulate exactly the dynamics of how these droplets move on surfaces. And you can also make particles that are propelling by themselves, particles that start rolling across surfaces, and that you could maybe use for some delivery technologies again. Here is a little video that was made by the BBC a few years ago. There's a droplet that's actually running up the hill. It's climbing up the hill. And the reason why it does that is because there is a very small micro patterning on the surface. There is this kind of sawtooth pattern. And every time that this droplet sinks down, it creates a little bit of steam, some vapor. And these puffs, they go down into the grooves, and they're pushing the air backwards, and as a result, the droplet is going forwards. and you can make the droplet go and run up the hill this way. So yeah, it's a really interesting effect that you can use for, yeah, like really fun little things. Now after our main course, it's time maybe to have some dessert. And as a dessert, we're going to bake a cake. And here, you know, we have this huge wedding cake. And yeah, the problem is that this does not fit into your oven, right? This is way too big to put in a single oven, and therefore we have to break it down into some smaller pieces. And there's also a reason why, because at your wedding, you want your cake to be perfect. You know, you want it to be very nice on the inside, on the outside. But if your cake is too big, then, you know, the outside might be, you know, beautiful and lovely, but maybe it's still like really soggy and awful on the inside. So then what you can do is you can measure the temperature at different locations inside the cake. Here we have a temperature sensor at location 1 in the middle, and then 2 and 3, you know, like getting closer to the edge, and then a 4th temperature sensor all the way on the outside of the cake. Oh, and this is the picture I wanted to show you earlier. So, you know, this is the bad wedding cake. This is what you really don't want, you know, when it's like nice on the outside, but like soggy and gooey on the inside. So now when we measure this temperature, then you can see the following things. That initially, you know, the black line shows the temperature on the outside. So it's going to start here on the left-hand side, and the temperature rises very quickly, and after 5-10 minutes, the outside is beautifully cooked. But then, if we look at, you know, the temperature on the inside, that's like the yellow line here, for example, it's going to take much longer. After 5 minutes, it's still cold on the inside, and after 10 minutes, it's really still cold, and it takes 15 minutes for this small little cake to heat up. And so, yeah, that really tells you something about how this heat is transferred into the cake, and then how you can optimize the transport of the heat, but also the baking of the cake itself. Now, after we've made our cake, maybe we can decorate it with some honey. And I'm going to show you a video from space. Here is an astronaut who is going to tell us about honey in space. Oh, I need to turn on the video. Can you hear it? Right, so if you look at honey in space, then you see it's not just a liquid anymore, right? It really looks like a much more complicated material. It has some elasticity in it as well. He says, you know, if you twist it this way, it starts to curl back. And so the properties of this material are very strange. And without gravity, you can really study that in detail. Here I'm going to show you another video of mixing honey. Or any other liquids that is very thick and viscous. So in this video we have 3 pieces of coloring agent, just some food dye, and we're going to try to mix these colors into the fluid.
Alright, now we're going to rotate.
So he's going to rotate this bath of liquid, and now he's going to stir these colors into the liquid. So 1 rotation, keeps going, 2nd rotation, and you can see that the colors are like really nicely mixing into the liquid now, right? I think he's going to keep going a little bit more. The 3rd rotation, keep going. Are you convinced it's well mixed? Okay, so he's turning the other way. 2, a few more, 3, 4. And look at that. It's coming back exactly where it started. So this is really a proof, a demonstration that it's very difficult to mix honey. You think that you are mixing it really well, but if you rotate the other way, it comes back exactly where it started. And so this is a problem for many different things. Like if you want to make a cake batter, or if you want to mix liquids at small length scales, then mixing is really very hard. Okay, now, and this shows you the same thing. The last thing that I want to talk about is making some coffee. Now, maybe you've already seen this before, but here's a coffee pot. There is some water down below. The coffee sits here in the middle, and then we're going to heat it from below, boil the water, and the boiling water goes through the coffee, and then it's going to end up at the top reservoir. Now, in this video, we're looking at the water not just with normal light, but instead with neutrons. And these neutrons, they're going straight through the metal, because this coffee pot is made of aluminium. But the neutrons, they don't see the aluminium, they go straight through it. But when the neutrons hit the water, they hit, and it turns into, the black colors over here. So you can actually see through the metal with these neutrons. And because we can see through the metal, we can see what's happening inside. So here we go, the water begins to boil, it goes through the coffee, and it ends up in this top reservoir. I think this movie was really expensive to make. They must have spent, a lot of neutrons for this. So, what's happening is that here in the middle we've got the coffee, right, and the water is going through. Now you can have 3 scenarios. Let's say that you put too much coffee grounds. You really stuff this, coffee pot with lots and lots of brown coffee. And then the water doesn't want to go through anymore. It's just too dense, and there are, maybe some very small little channels where the water can try to percolate through, but in the end it's going to hit a dead end and the water cannot get through. On the other hand, you can have the other scenario here on the right-hand side, where you only put like 1 or 2 spoons of coffee, and then the water will definitely go through, but it's going to be very, very bad coffee. This is the kind of coffee you get at an American gas station. So, so that's the coffee I'm used to. Now, it turns out that, if there are any Italians in the room, they are given some kind of magical ability to know precisely where this magical point in the middle is. That point in the middle is what we call the percolation transition. That's where the water can just about go through, and at the same time it's still a very nice and a thick, dense coffee. And so that percolation point happens in many different, many different scenarios on this planet. It's useful for making coffee, but it's also used to predict forest fires. So if you have maybe one tree, then it can set fire to the next tree and the next tree. And if these trees are far away from each other, you don't have percolation, and then you are safe. And if the trees are closer to each other, then the fire will propagate. You can also think of infection dynamics. Maybe one person has a certain illness, and then it can pass that illness to someone else, and to someone else again. So if the density of the people is, very large, then you will have infection, and if the density is low, then you will not have percolation. So this theory of percolation is used in many different areas and many different fields around the world. And here you can see an example, again from nanotechnology. We're looking at carbon nanotubes, and we're looking at the probability of percolation for the density of these nanotubes in the network. Again, if you have a low density, you don't see connectivity, and if you have a very high density, then the signals can pass through here. Now, once we've made our coffee, then maybe we can decorate it a little bit. So here you see a picture of this latte art, and if you go to a nice coffee shop, then the barista will be making some beautiful patterns on top of your milk. Now, as a physicist, I like to think about this in terms of some key variables that I can change. So on the one hand, I can change maybe, like the velocity, how quickly am I pouring my milk down into the coffee. I can also change the height of my milk jug, or I can change the radius of my milk jet. So these are three, main properties that I can change. And I can go one step further, and I can create some dimensionless numbers, some ratios between these numbers that I can vary. So the first number is called the fruit number. And that tells you something about the importance of gravity and the energy that you put in. So you can think of this a little bit like an inverted fountain. Normally for a fountain you have water, you push it up into the air and it falls back down again because of gravity. Here you've got a light liquid. The milk wants to float upwards, but you're trying to push it down into this, heavier coffee. So the fountain goes down, but then because of gravity, because of buoyancy, the milk jet comes back up again. And the more energy you put in, the deeper the fountain can go. And that leads to more mixing. And so on the left-hand side, if you have a shallow fountain, you're going to have white colors because all the milk stays at the top. And if you have a very deep fountain, then you're going to have a brown color on top because you have more mixing. Oh, I'm going to turn this off. Okay, good. Another thing that you can change is the Reynolds number. And the Reynolds number tells you something about turbulence. So if you go to low Reynolds numbers, then everything is still in a laminar regime, and then the fountain gets deeper and deeper and deeper. But then you add more turbulence to the system, and then it turns out that the fountain actually gets shallower again. So it's a very strange behavior. And because of that, it's really complicated. And the barista somehow knows by moving this cup around onto the coffee to really perfectly tune between these different fountain parameters. There are also some other ways to make coffee. One famous method is called Turkish coffee. And Turkish coffee is really very fine particles that are slowly sedimenting down to the bottom of the coffee cup. And if you look very closely, you will see that these coffee particles, they will start touching each other. And then they form these really beautiful patterns. This is sometimes called a kissing pattern as well. Or maybe you're familiar with this one, right? The French press. So really you just, throw in some hot water, throw in some coffee, and you push this big filter down, and then you can drink the coffee afterwards. Now, you may have seen that if you try to push this too hard, then suddenly it will jam, and then all the coffee will fly into your face, and it's absolutely awful. And so you want to prevent this from happening, but if you push too slowly, then you can wait for hours and hours, and it will just take a long time before you can eventually drink your coffee. So what you want to do is to find the perfect amount of force that's required to just maximize the time or minimize the time that is used for your coffee making. And then one other thing that you can do is you can make a latte, in this case a layered latte. So before we had the coffee and we were pouring the milk inside, you can also do the other way around. You can start with the milk and you can pour the coffee inside from the top. And then what you see is that you get these really beautiful layers that start forming inside your glass. The best way to do this, I think, is in a very tall glass, and then really like pouring a shot of espresso in from the top. So maybe you can try this at home. And then, once you've made your coffee, sometimes you can spill the coffee. So you get a little coffee drop that sits on your desk, and maybe you've seen this, that this coffee starts evaporating, and then what happens is that all the particles, they start flowing to the edge. And as a result, you get these coffee rings. In this case, a little heart shape. Where at the edge, you get a very high concentration of coffee particles, and in the middle you have a very low concentration. Now this coffee ring effect is actually very bad in nanotechnology, because what you would like to do there is often to create some kind of a coating, and the coating has to be nice and uniform. So you want the concentration of the particles to be the same everywhere over the whole surface. So really what you want to do is you want to prevent this coffee ring effect. And it turns out that you can do that. You can do that by adding some very small fibers to this liquid. They're called nanofibers, and you can use different materials, maybe cellulose nanofibers. And then if you increase the concentration of those fibers, you can see that the coffee ring here on the top is slowly fading out and is turning into a very nice and even coating. And so, yeah, this is a very important thing to control in these types of technologies. So I think I'm done. This is all I had to say. I would like to say thanks to my friends and co-authors of this work, so Maciek and also Vivek and Andre. This is now going to be published maybe tomorrow or the day after tomorrow in Reviews of Modern Physics, and so in the next few days this will actually be officially online. But you can already have a little look. A preprint is available on the archive, and that's the archive number over here. The structure that I discussed in my talk today is very much like the structure of this paper. We start with some kitchen sink fundamentals, the things that you can observe in the kitchen when you wash your hands. Then we talk about maybe some drinks and cocktails, starters and soups, the main courses, the desserts, coffee, tea, and eventually we talk about washing the dishes. So all of the things that I talked about today, you can find in more detail in this paper. So with that, I say thank you very much for listening. I'm very happy to take questions.
So let's see whether there are any questions. Okay, there's plenty. Good. Let's put here.
So first of all, thank you very much for this beautiful lecture. Very tasteful, yeah. I have two questions. So first of all, I assume your area of expertise is physics of liquids. I would like to ask if you explore any other interesting areas in physics. And the second question is, some time ago I was interested in manned mission to Mars, and there was a discussion on the internet. Somebody was arguing that the landing on Mars is specifically difficult because there is a lot of dust on the surface. And the concern was that our physics of dust and bulk materials is very poor, is not very good. So did you have a chance to work with physics of dust so far? Is it difficult? It is close to maybe physics of liquids some way. What do you tell us about it?
So really nice questions. Thank you very much. So maybe I will start with your second question. The physics of dust. I have never worked on that myself, but I think there is a lot to explore in this area, because on the one hand it uses the aerodynamics of flows that are generated in the air itself, and then you also have particles themselves that are interacting with each other in terms of granular matter. We do talk a little bit about granular materials in this paper as well. Maybe an example that you are familiar with is if you have, let's say, a silo or a machine like this, and you have all coffee beans inside. And then the coffee beans, they start flowing through this silo. And at some point they get stuck in this little hole. And if you move it outward a little bit, they start flowing, and if you bring it inwards, then suddenly they really immediately stop flowing. Similarly, if you have a sand clock, works in the same way, right? And so when you look at the flows exactly at that small little point here, is very critical. because what's happening there is basically a jamming transition. And this is not well understood, because people have studied the physics of jamming and the physics of glassy materials, but now everything is flowing and everything is moving. And as far as I know, we do not know how to answer these questions exactly. So yeah, I think this is a really nice and important thing to study because of the space physics that we want to explore. Your first question is, you know, what I've worked on myself, and my background is in physics and biology, and so most of my research is you know, between those two areas. And what I like about is that you can combine two different fields, and you can combine ideas from biology and physics with each other. But I think the same is happening over here in food science as well, because there you have a lot of chemistry, you have a lot of biology, because many of the things that we eat, you know, like, are either living or have lived in the past. And so really, yeah, it's an opportunity to combine different areas of research with each other in terms of nanotechnology or unexpected things that are actually much more related than you initially thought. And so, yeah, I really hope that in the future we can also have programs in physics departments that try to connect physics with many other disciplines. More questions?
Yeah, so I have a question concerned with latte art, actually. I've heard people claim that there is a noticeable difference when you steam milk and when you froth it. And, like, is there any, you know, physical signs that this might be true?
Yeah, so the question is about latte art and whether there is a difference between steaming milk and frothing milk. Now, to my knowledge, and I'm really not an expert in that in particular, is that what you have is you have some milk, right, in a cup, and then you have some kind of nozzle from your espresso machine, and the steam comes out of the nozzle, and then you try to mix the steam with the milk, and then you get this very nice foam that is very smooth and very creamy. And then this creamy milk foam you can then combine with your coffee to make these beautiful swan-shaped structures, for example. Now, what I think is important is that when you bring this steam into the milk, that you entrain a lot of air, because the air is going to make all these little micro bubbles. And the smaller the bubbles, the creamier they're going to taste. And that means that you need a lot of energy, because it takes energy to make these micro bubbles. And if you just, you know, put the steam straight down into the milk without any air, then you're going to heat up the milk and you're going to get some large bubbles, but not the same nice little microstructures that you're looking for, that are these creamy, tasty bubbles. So I think that's the difference, that this frothing really involves creating flows that entrain air and create microstructures.
Thank you.
Any other questions? Well, if this is not the case, let's thank Arnold again.
Okay, thanks very much.
And have a good evening.